When a complex compound AI system attempts a multi-step coding task and fails compilation, it generates a massive, highly detailed trace of its execution and errors. Standard RL algorithms, like GRPO, process this failure by discarding the text entirely. They collapse the rich compiler log into a sparse scalar reward of 0. That single integer is then fed back to mathematically adjust a massive matrix of neural network weights. Deriving an accurate policy gradient from such a sparse binary signal requires tens, sometimes hundreds of thousands of trial and error rollouts before the system adapts. Large language models already possess a native, highly sophisticated ability to comprehend rich natural language and diagnostic text. Engineers are actively destroying highly descriptive textual error logs to train systems that are explicitly built to read and understand text. Forcing language models to learn via collapsed scalar matrix introduces a lossy translation layer, making the adaptation of complex pipelines computationally prohibitive. The GEPA architecture, short for Genetic-Pareto, eliminates the need for policy gradients entirely. Instead of updating the underlying mathematical weights of the model, GEPA optimizes the natural language instructions, or prompts, of individual modules. When GEPA encounters a compilation failure, it consumes the exact same error log, but rather than converting it to a 0, it processes the log natively as diagnostic language input. Across standard benchmarks, GEPA outperforms GRPO by up to 20%, while requiring up to 35 times fewer rollouts to achieve adaptation. Natural language reflection provides a significantly higher leverage gradient for adapting compound AI systems than mathematical weight updates. The GEPA pipeline begins its optimization loop with Phase 1, diagnostic tracing, executed during a stochastic mini-batch rollout. The algorithm records the system's full execution trajectory, securely capturing intermediate reasoning chains, API tool calls, and the inputs for every module. It then generates an evaluation trace. This trace intercepts the environment's raw textual feedback, like human grader rationales or compiler alerts, before the environment collapses them into a numerical score. Once the data is collected, GEPA initiates Phase 2, implicit credit assignment, driven by a dedicated reflection language model. This reflection model parses the trajectory and the evaluation trace to perform root cause analysis, isolating exactly which submodule in the compound system is responsible for the failure. This document compares a minimal seed prompt with a GEPA-optimized prompt for a multi-hop retrieval system. Notice the explicit rule generated under key observations and lessons, which strictly prevents the system from merely restating known facts. Further down in the practical strategy block, GEPA has generated a precise mental model, instructing the module exactly how to hunt for missing, logically linked entities. These granular, context-aware textual additions directly neutralize the specific retrieval errors logged in the evaluation trace. Reflective text mutations apply targeted, high-level cognitive corrections that thousands of stochastic scalar weight updates could never effectively isolate. Standard prompt optimization algorithms often fail due to a structural vulnerability, the local minimum trap. By optimizing greedily for a single global best prompt, the search algorithm rapidly plateaus, wasting its remaining rollout budget on dead-end variations of the same instruction. To counteract this, Phase 3 of the GPEP architecture employs Pareto-based candidate selection to enforce evolutionary diversity. This schematic illustrates how GPEP tracks candidate success against specific training tasks within a scores matrix. The algorithm identifies the highest scoring candidate for each individual training instance, assembling a multi-objective frontier. Candidates that are strictly dominated, meaning they fail to achieve top performance on any specific task, are permanently deleted from the pool. GEPA then stochastically samples candidates from this surviving frontier, weighting its selection based on how frequently a candidate achieves top performance across the dataset. Selected candidates undergo one of two evolution strategies: single candidate reflective mutation or two candidate systemic merging. During merging, specialized rules from two different Pareto optimal prompts are surgically combined into a new, highly effective single iteration. Maintaining a multi-objective Pareto front guarantees genetic diversity. It prevents the algorithm from stalling and ensures robust generalization across edge cases. The theoretical advantages of this architecture are validated by empirical benchmarking running on the Qwen3-8B model. Across 6 distinct reasoning and coding benchmarks, GEPA demonstrates a 6% average gain over GRPO. An optimization test on iFinch, an instruction-following dataset, clearly illustrates the disparity in sample efficiency. This chart tracks test set scores against the number of rollouts. The baseline GRPO learning trajectory requires 24,000 rollouts to eventually cross the 35% test set score threshold. In contrast, the GEPA trajectory spikes almost vertically on the left side of the chart. It hits a superior score of 38.61% and terminates its search at only 678 rollouts. GEPA also outpaces the prior state-of-the-art prompt optimizer, MIPROv2, generating over double the aggregate performance gains and yielding a 12% accuracy jump on the AIM 2025 math dataset. Translating execution traces into text-based genetic mutations effectively bypasses the sample inefficiency curve inherent to verifiable reward algorithms. Deploying production AI involves strict constraints, limited inference budgets, expensive API toll booths, unable to fine-tune locked weights. Under these conditions, relying on opaque, scalar policy gradients to teach systems that already possess a mastery of language is an architectural dead end. By utilizing GPA's reflective prompt evolution, engineers can finally transform expensive trial-and-error rollouts into deliberate, highly leveraged learning. The theoretical advantages of this architecture are validated by empirical benchmarking running on the Qwen3-8B model. Across 6 distinct reasoning and coding benchmarks, GPA demonstrates a 6% average gain over GRPO. An optimization test on iFinch, an instruction-following dataset, clearly illustrates the disparity in sample efficiency. This chart tracks test set scores against rollouts. The GRPO trajectory requires 24,000 rollouts to cross the 35% threshold. In contrast, the GEPA trajectory spikes vertically, hitting a 38.61% score and terminates at only 678 rollouts. GEPA also outpaces the prior state-of-the-art prompt optimizer, MIPROv2, generating over double the aggregate performance gains and yielding a 12% accuracy jump on the AMI 2025 math dataset. Translating execution traces into text-based genetic mutations effectively bypasses the sample inefficiency curve inherent to verifiable reward algorithms. Deploying production AI involves strict constraints, limited inference budgets, expensive API toll booths, and locked weights of frontier models. Under these conditions, relying on opaque, scalar policy gradients to teach systems that already possess a mastery of language is an architectural dead end. By utilizing reflective prompt evolution, engineers can transform expensive trial-and-error rollouts into deliberate, highly leveraged learning.